begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students who just pray with us today. Help us to just glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so glad you guys are working on your homework. That is a happy thing for me. So I need to start with a proof of the thing you're using. Well, actually not that. Let's start with lemma 3.3.1. Just to let you know where we're going. Hopefully this week I will basically cover as much as I can of chapter 3 of the notes, which I have now posted. So it's roughly in tune with chapter 2 of Curtis, right? But here's my lemma 3.31. Let V be a vector space over a field so we'll use this notation, okay? This notation means that V is a vector space over the field F, all right? I didn't write that in the notes, but that's pretty common notation, and it'll save me. Well, if you read my notes, about the 30th time you read let V be a vector space over the field F, you'll get tired of it. And my shoulder hurts, so I got to write less. All right, so there we go. The F linear combination of F linear combinations of vectors from S, where S is some subset of V, okay, is once more a F linear combo of vectors in S. All right. So the text has some kind of inductive proof here. I'm going to give you a slightly more direct proof that's based on some calculational techniques. So here's the proof. First of all, I'm going to let S be a finite set here. Let's see here. S1, S2, Sk, let's say. So you have S as a set of vectors. Oh, I'm sorry, I've already messed it up. Sorry, I get wrapped up in the notation here. So what I'm going to do is I'm going to let Tij denote the vectors in S. I'm sorry. It took me a while to find notation that makes this short enough to write that it's not annoying. So here it is. Let me try this again here. So let Si equal to a sum j equals 1 to n sub I of Cij Tij. So here Cij are our scalars in the field, and the Tijs are vectors in S. I actually don't care how many vectors there are in S. The point is I have to look at finite linear combinations. If S could even be an infinite set. Fair enough. All right, and this is for, of course, for n sub I and I being integers, positive integers, with I equals to 1 to k. So this is for n sub I and I in n, and I equals to 1 to k. I guess that's a little bit redundant. Anyway, let's let B1, B2, bk be in the field, and consider the following. So what I'm going to look at is the sum I equals 1 to k of bi si. So what is that? Why am I doing this? I'm looking at an F linear combination, right, of these S sub i's. What are S sub i's? How have I formed the SI's? Yeah, they're a F-weighted sum of vectors from S. In other words, each S sub I is a linear combination of vectors in S, right? So I'm looking at exactly what I'm supposed to look at, a linear combination of an F linear combination. Now all I do is just write it out. So, all right, we got the sum I equals 1 to k, bi sum, and let's see, si was the sum j equals 1 to ni n sub I of cij, tij, right? Now what I do is I simply use properties of finite sums to bring the constant inside. So I got myself a sum I equals 1 to k, sum j equals 1 to n sub I of what? Of b sub I, c sub ij, t sub ij. But what is that? This is the product of elements in F, right? So that's a scalar for each choice of I and j. And how about tij? What are these? Those are elements of S. And this is a linear combination with finitely many terms, because if you take two finite sums and iterate them, you still only have finitely many terms, right? The counting doesn't really concern me. It's still finitely many terms, the weighted sum over F. In other words, this is a F linear combination. So this is once more a F linear combo of elements of S. And so we're done. Now Curtis, when he argues things, he shies away from this sort of notation, and he'll kind of choose a more simple notation and give you some sort of induction argument. And we'll do some of those in here, but not right now. So that brings me to the definition, which you've seen before, but let's see it again. Let S equal to, say, V1, Vk, some subset of vectors over a vector space with field F, then span S is what? How do we define span S? It's the sum, right? I equals 1 to k of ci vi such that what? Oh no, I found a typo. I won't say what it is though. I want to give you guys a chance to email. Let's see here. Ci and f such that for I equals 1 to k. Yeah. Now, we already did this, right? But when I did it before, it was in a less abstract context. I defined the span of column vectors before. Or maybe I defined it more generally. But anyway, this definitely, well, I guess I might have defined the span over like a ring. But still there, I forget what I did before, but this we'll do now. It doesn't really much matter what I did before, does it? Well, I guess it does. Eventually I will find the color I'm looking for. Haha. It must be in this handful. Any questions? In other words, the span is the set of all finite linear combinations from S. A little bit more fine print. If S is an infinite set, then span S is the it's the still the set of all finite linear combinations from S. So that's the infinite case, all right? And what else? What is another exceptional case we might think about? What if S is the empty set? What's the span of the empty set defined to be? Exactly. Yeah, the zero vector. All right, so that's the concept of a span. Now this set S is called the generating set. All right. So if you say W is equal to the span S, then you know if I said this thing was equal to W, let's say, all right, that would make S a generating set. A generating set for W. In this case, we'd also say that W is finitely generated. And that brings us to the theorem. That's really nice. That's if V is a vector space over a field F, and S is a subset of V, then the span of S is a subspace of V. So how do we prove this? Oh, by the way, try to make sure that the camera is not showing like above and below. Like we want to try to keep it zoomed in at like the level of just the board, because if it's a little bit further back, it's hard to read stuff. I forget to tell you guys this stuff. Anyway, so what do we do? First of all, let's take care of one case. If S is equal to the empty set, then the span of S is what? The span of S is just 0, which is, by the way, a subspace of V, so we're done. Otherwise what? Otherwise S is non-empty, right? And so you can say let X and Y be elements of the span of S, right? And you can take C an element of the field, right? Observe that Cx plus Y is a F linear combo of what? Of F linear combos, right? Therefore, hence, by lemma 3.31, Cx plus Y is once more an element of the span of S because, well, it's again a linear combination of the elements in S. Therefore, by the subspace test, we're what? We're almost done. What do we need more? We need more, right? What else do we need? We need that the span of S is non-empty. So how can you show me that the span of S is non-empty? Can you tell me something that's in the span of S? Right. So if X exists, right, which we need, which that's S being non-empty means that there exists an S, right? So S not equal to the empty set implies that there exists X in S, right? Therefore, 1 times X is an element of the span S, which is not the empty set. See, because 1 times X is a linear combination of X, I mean, I'm using x in a different sense in the previous sentence and in that sentence, but here, if you want, I can make it different. There, better. Therefore, by the subspace test, we have that the span is a subspace. All right. Any questions? Why am I using that smudge thing? It's just a smudger. It's not an eraser. Where's my juice? Oh, thank you. Here, let me just look at a couple of examples with you guys. So, let's see here. Example, we could have W equal to something like, I don't know, S plus T, comma, S, comma, T, such that, oh, I already have that example in the notes. Let me look at something more exotic. This one's too easy. Let's look at something more fun. How about this? T, S plus T, T, and S, such that T and S are elements of the reals. I'll keep it real. Now, my point to you is that it's easy to rewrite this using properties of matrix. That this is T times what matrix plus S times what matrix, such that T and S are arbitrary real numbers. What's up? I got a 1, 1, 1, 0. Right. In other words, check it out. This is the span of 1, 1, 1, 0, 0, 1, 0, 1. So if I want to prove that W is a subspace, all I have to do is do what I just did, write that down, and then I go, bam, subspace of R2 by 2 as W is formed by a span. So this theorem is very nice, right? Agree? Look, you could even go back and you could an infinite example that you could use this span notation for. I introduced to you guys last time the polynomials in X over the reals, right? So another way you could write that is this. It's the span of 1, x, x squared, x cubed, and, well, you get the idea. See, those are polynomials. What's the difference between a polynomial and a series? A series could have infinitely many non-zero terms. Polynomial, by definition, is formed with finitely many non-zero terms. But of course, that's exactly what the span does. It's the set of all finite linear combinations of those elements. Those are exactly polynomials. Just what I said. It's polynomials in X with real coefficients. For example, while we're at it, and I added this to the notes, you could do like this. This would be polynomials in 2 variables, which you could define as follows. So, for example, something like you have coefficient of, well, let me write it out here. So, for example, you have something like 1 plus x squared times y plus x cubed times y squared. This would be something in here. and we multiply that out, you've got a polynomial in 2 variables. So you can even use this notation to build wackier things that I didn't get to last class. That makes for some nice examples later. But anyway, sorry. I should have, well, I'll behave and go on and not rub any more salt in that wound at the moment. Yeah, so this span theorem is ever so very useful. That brings us to the concept of, I believe that's about all I got. I mean, I've got some more examples in the notes, which I could give you, I suppose. Oh, fine. We have time for another example. We'll go with 2 more examples. If you look at the differential equation, y prime 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 plus 3y prime prime plus 3y prime plus y equals to 0, what you'll find is that the solution has the form y is equal to c1 e to the x plus c1 x e to the x. Oh, I'm sorry, did I say x? I meant minus x. Plus c, that's c2, plus c3 x squared e to the minus x. Now, of course, you don't have to know that because this is differential equations that I'm doing right now, right? But my point to you is this is something we learn in differential equations. And so this is basically an arbitrary element of the solution set. Arbitrary solution of star has this form, right? In other words, you can write that the solution set to that differential equation has the following form. It's nothing more than the span of e to the minus x, x e to the minus x, x squared e to the minus x, right? So in other words, the solution set is a subspace of the set of functions from R to R. So it's another example of a span. In fact, our general solution to a differential equation comes out as a span of so-called fundamental solutions. Fundamental solutions, well, that's a technical term from differential equations, but I'll just leave it there. Now, another example, yeah?
What is the asterisk?
Oh, very, very, very fair question, Christina. Star. Sorry, yeah. I was doing name calling, but I neglected to attach the name. So it's the differential equation. No, duh. I was checking that this actually is a solution for a second, and I got confused. But what happens is you get like plus 3 minus 3, and then minus 3 plus 1, and they like cancel in pairs when you plug in the e to the minus x. Another example, which is actually an example of examples, and so this next example I'm going to give you introduces some important, it gives you some important, very important subspaces which are formed by spans. So this isn't really as much of an example as it is as introduction to the fundamental, let's just say fun subspaces associated to an element of your m by n matrices over a field. There are 3 fundamental subspaces associated to a given matrix, m by n matrix: the column space, the row space, and the null space. So let me just throw them out here. So this is the definition. The so-called column space of A is exactly, it is the span of column j of A, and this is a notation we can use sometimes. J equals 1 to what? How many columns are there in a m by n matrix? N, as in nanu nanu. So there you go, n. So this is just like a fast way of writing column 1, comma column 2, comma column 3, comma dot 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 column n. All right. The row space of A is the span of row sub I of A, I equals to 1 to m, as in mummy. Now, are they subspaces? Right? It's like shooting fish in a barrel with this thing, right? Oh, I'm sorry. If I'm from Washington State, I wouldn't say such a thing. It's inhumane. But let's see here. I just threw that in there, just for fun. I'm sorry. I shouldn't pick on said person because she has been very nice to me this semester. Let's see here. Where am I? Oh, you're waiting. You're biding your time. All right. Treating me like the fish. I think if you think about each column in an m by n matrix, it has height m, right? There are n columns, but each one of them only has as many as there are rows, right? So that's actually a subspace of Fm. This is a subspace of F1 by n because it's a row. And then finally, the third fundamental subspace associated with the matrix is the so-called null space of A. This can be written as a span, but not without work. But what this is it's a solution set. It's x in Fn such that Ax is equal to 0. Now, obviously, you don't want to use the span theorem to show that that's a subspace. How are you going to show that this is a subspace of what? By subspace test, all right? How would you prove the null space of A is a subspace by the subspace test? So the proof is really not hard, right? Just let x and y be in the null space of A, and C be something in the field, and then consider A times, say, Cx plus y. By properties of matrix multiplication, we have what? C times Ax plus Ay. That's matrix algebra, right? And then what do you have? Right, C times 0 plus 0, because we assume that x and y were in the null space of A, right? Which means that when A hits them, they die. They become 0. So, like the fish. And so that's 0, right? So thus, Cx plus y is an element of the null space of A, and then hence by subspace theorem. Well, I guess fine. I'm missing some detail. How do I know that the null space of A is non-empty? How about A times 0? 0, right? So therefore 0 is an element of the null space of A, which is non-empty. And x and y in the null space of A implies what? X plus y, and Cx is in the null space of A for all C. Therefore, by subspace test, null space of A is a subspace of Fn. So there you have it. These are the three fundamental subspaces associated with the matrix, and here's why each one of them is in fact a subspace. All right. Okay. So hopefully, now we're starting to have a good collection of examples of subspaces to work with, right? Somewhat varied differential equations, just simple matrix examples, whatever. Those integral things you had in your homework. There's lots of them, right? So this brings us to the concept of the next chapter in this story we're telling is that of linear independence. Okay, so what is linear independence? Well, we already talked about it, right? So, I mean, we talked about it where? Let's see here. S, a subset of the vector space V over a field F, is linearly independent if and only if there does not exist a linear dependence amongst the elements of S. And I'm missing a term. What am I missing? Important term. Non-trivial, right? In fact, we can prove that if a set of vectors is linearly independent, the only linear dependence it emits is the trivial dependence. What is the trivial dependence? So here's a what I call it, proposition theorem. We still need to take a vote on all these. At the moment, this is called a proposition. Proposition 3.4.3. And it's the following statement: S, subset of a vector space or a field F is linearly independent if and only if, for each set of constants, C1, C2, Ck in F, C1 and curses. I wanted to let S have elements. Let's say S is equal to V1, V2, Vk, all right? C1, V1 plus C2, V2, these are the V1 through Vk are the elements of S, all right? Plus Ck, Vk equals to 0, right? So if there exist constants in the field C1 through Ck, and a linear combination of those constants times those vectors is equal to 0, it implies, all right, this implies what? It implies that C1 is equal to 0, C2 is equal to 0, and so forth. Ck is equal to 0. In other words, like I was just saying in words, what this is saying is that if a set of vectors is linearly independent, the only possible, trivial, how to say this, the only possible dependence between them is the trivial dependence, all right, in the sense that if I have it equal to 0, it forces all the constants to be 0. This is actually what we tend to use to measure linear independence of a given set. What you do is you just set a linear combination of them equal to 0, and you prove that those coefficients must be 0, then that gives you linear independence. So this is our go-to calculational tool to check linear independence. So how do we prove this theorem, this proposition? Here's the proof. All right, so assume S equals to V1, Vk is linearly independent. All right. So suppose there exists a non-trivial linear dependence. No, that's not what I want. Let me be more precise here, sorry. Suppose there exists C1, C2, CK in F such that C1v1 plus C2v2 plus CK vk is equal to 0, but there exists Cj not equal to 0 for at least one j in the index 1 through k. So that would be, if we can, you see what I'm doing here? What would that mean? So I'm assuming that you've got a linearly independent set, right? I'm assuming that its linear combination is equal to 0, right? And then I'm assuming that this doesn't happen. This is proof. I'm doing a contradiction proof, right? Remember, that's how we negate an implication. Assume that the start is true, but the end is false, right? Okay. Anyway, what we got? What does that mean you can do? If Cj is not equal to 0, what can we do? We're in a field. A non-zero thing. We can divide by it, right? So that condition that Cj is not equal to 0 means we can solve for Vj. So solve for Vj. Let me be more explicit about that. So let's call this thing star. So solve star for Vj. What do we get? Vj is equal to what? It's equal to minus C1 over Cj, right? V1, minus C2 over Cj, V2, minus minus Cj over Cj, Vj. That is omitted, all right? Minus Ck over Cj, Vk. So this notation, you put a hat on it. That's a hat you don't want to wear. If you wear that hat, you're gone. You're not even there. You're deleted from the list, right? So if I was to have such a hat and put it on Lorenzo, yeah, she'd be gone. She wouldn't even be. There wouldn't even be a corpse. It would just be nothingness, like just cease to exist. Not even in the list. So yes, we do not want to wear this hat. But there it is. So that's just a convenient notation to say that's gone. Everything else is there but that, right? And what is that? Yeah, I solved for Vj. What is that though? Like in words, this says that Vj is a non-trivial linear combination, right, of everything else. I know it's non-trivial because I know Vj is not equal to 0, right? We already proved last time that, we can assume that the vectors in the set are non-zero. If the vectors in the set are 0, it's linearly dependent. We can make a separate proof of that, right? So I can reasonably assume, I should reasonably assume that fine. There, now I have earned the right to assume it by adding the assumption. All right. Anyway, my point is, if this is non-zero, certainly that's non-zero, right? That says that Vj is a linear combination of the other vectors. So what does that mean? That means there's a linear dependence in S. But what did we say about S? S is linearly independent. That's a contradiction. Consequently, there cannot exist even one Cj, which is non-zero, given linear independence of the set. Does that make sense? So that's terribly useful to us because we can use this to check linear independence of sets. All right. These are really boring in some sense, like this set right here is linearly independent. How do I know that? How do I know that this set right here is linearly independent? If I set that equal to 0, what do I get? I get 4 equations, right? I encourage you to cherry pick the ones that are useful to you. And then I also know that C1 plus C2 is equal to 0, which implies that C2 is equal to 0. So there you go. If I take this linear combination of matrices, I set it equal to the 0 matrix, that immediately implies that the coefficients in linear combination are both identically 0. Consequently, this matrix and this set I'm about to box, this one here, not the span. Spans are linearly dependent by construction. They include all possible linear dependencies of the things you're putting into it. But setting aside the span, right, this is a linearly independent set, subset of the 2 by 2 matrices of reals. Yep. Oh, thank you. Yeah. Oh, man. So I didn't need to work so hard, right? Scratch that. This and this immediately gives me C2 equals 0. So we didn't even need to do algebra in this case. You just immediate. Can you think of any other examples that are obviously linearly independent? This set, actually, setting aside the span, is linearly independent. But that's a longer discussion, because it might seem to you, some of you, that those are just multiples of x, right? So it seems like they're dependent on each other. But that's an illusion. That's not the kind of linear. You're not allowed multiples of x in this discussion. I need to come back to that some other day. I can talk about it longer. Some other examples of linearly independent sets would be, for example, in Fn, we have this set, E1, E2, En. Or in F, M by N, we have the set Eij, right? Such that 1 less than or equal to I less than or equal to M, 1 less than or equal to J less than or equal to N. These are linearly independent sets, right? You can see that pretty simply if I take C1, E1, right? Plus, I think I talked about this the other day. I'm sorry, I'm repeating myself. Well, that's exactly C1, Cn, right? So if I set this as 0, it immediately implies what? All the coefficients are 0, right? And a similar calculation will show that the matrix units are also linearly independent. All right? All right. So the bigger problem we're facing this week, all right, guys, is the question of when something is not linearly independent, right? When something has some linear dependence, how can you modify it in such a way to make it linearly independent, all right? Or another question, if you have a set which is, say, linearly independent, but it doesn't get the whole space when you span, you know, how do you get what else is left there? Now, both of these lead to the concept of what's known as a basis. Okay, so a basis is what we're going to be talking about a lot next time. So a basis, if we have a vector space V, or even a subspace of a vector space, I'll just say a vector space V over F, then if beta, which is V1 through, let's say, Vn, is a linearly independent set for which the span of beta is equal to the whole vector space, then beta is a basis for V. So the basis of a vector space gives us these like sort of fundamental building blocks that we can build a vector space with. And well, there's another property of linearly independent sets which is so important, which is tied into this idea, which is that, you know, if I had two things here, let me just say, suppose I had like a1 v1 plus da 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 plus, you know, ak vk, and I had that equal to b1 v1 plus da 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 plus bk vk. What do you get to say about the a sub 1s and b sub 1s and b sub k's and v sub k, a sub k's? What do you if it's a basis, if, you know, rather if it's linearly independent here, linear independence of this set implies that you can equate coefficients. Okay, so what that means then is in the vector space, all right, if I have something like x is equal to x is equal to something like x1 v1 plus x2 v2 plus da 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 plus xk vk vn xn vn for some x1 x2 da da xn in the field, it says that these coefficients are uniquely given, you see, because if you had another set of coefficients that also gave you back x, they'd have to be the same because we can equate coefficients for a linearly independent set. These coefficients are important. They're called the coordinate vector of x. So x, coordinate vector with respect to beta is equal to x1, x2, da, 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 xn. This is the coordinate vector of x with respect to that basis. All right. The basis is ordered. So that in other words, v1 has to come first, v2 has to come second, and so forth. Just to give you a simple example of this, and then I'll stop for today. Right here, keeping with this, since this is a linearly independent subset of this subspace W, in fact, I can say that this set, beta, well, W is the span of beta, all right? And if I was to look at, say, the vector A, which is a matrix, if I would say to A was equal to, say, I don't know, 3 times 1, 1, 1, 0, plus 2 times 0, 1, 0, 1. In other words, this matrix is 3, 5, 3, 5. Okay, that's an element of W. And the coordinate vector of A, all right, see, W is a set of 2 by 2 matrices, right? But it's actually what's called a 2-dimensional vector space. It's essentially a plane of matrices inside this set of 2 by 2 matrices. And what this calculation shows, and what we're going to try to understand this week, is that essentially W is just a copy of 2 vectors, and in fact, its coordinates are just those numbers. So the coordinate vector with respect to this basis is just 3, 2. So this is what we want to understand in the next 2 lectures, really. What is a basis? How do you construct them? How do you work with them? What are their properties? And one of the first things we're going to work pretty hard to show next time is that the number of vectors in a basis isn't up for grabs. It is the fact that has a basis with 2 elements in it. I can't find another basis with 3 or 1. That 2 is an invariant, is a characteristic of W. Can't change it. Anyway, I shut up. Thanks, guys.